Welcome, ladies and gentlemen. This is the video on phase diagrams, the fourth of our series of videos for intermolecular forces of attraction. In this video, our goal is to be able to correctly identify the regions on the phase diagram and read all pertinent information from a phase diagram. Essentially, we're becoming acquainted with a new type of diagram and understanding how to read it. Before we get to the phase diagram, though, however, there are several definitions that we need to go over. First is critical temperature and critical pressure. This has to do with phase changes of substances and recognizing that we get to a point where our substance can no longer exist as a liquid, meaning no matter what the no matter what the temperature, no matter what the pressure, you simply cannot essentially keep the molecules together anymore. And critical temperature is the highest temperature at which the substance can exist as a liquid. Basically, what is the absolute last temperature, regardless of pressure, where the substance can be held together. And the critical pressure is the pressure needed at the critical temperature to keep your molecules together, to keep them condensed in the liquid phase. And there's absolutely a relationship with intermolecular forces of attraction here. The stronger the intermolecular forces of attraction, the easier it will be to liquefy something, meaning the critical temperature will become higher and higher and higher, which should make sense to you, right? It should make sense that the more attraction particles have, the larger their critical temperature will be. Basically, the higher will be that threshold at which they can no longer essentially stay together, right? If they're more attracted, then they can stay together at a higher temperature. Melting point, which we haven't actually mentioned, we've talked about boiling point, but not melting point. But melting point is actually determined by the vapor pressure of the solid and the liquid. So technically speaking, melting point is not just the temperature at which something melts. Instead, it's the temperature at which the vapor pressure of the solid is equal to the vapor pressure of the liquid. And yes, solids can actually have vapor pressures. Solids can vaporize just a little bit. Their vapor pressures are incredibly low, but when you get up to the melting point, that's when the vapor pressure of the solid becomes equal to the vapor pressure of the liquid, not the external pressure. But what I want to point out here is that melting, we have a pressure component. There's a pressure component to melting. Boiling point we've seen before. We've seen this definition before. I'm just reminding you of it because it's going to be important for us. Remember that boiling is only reached when the vapor pressure of the liquid is equal to the external atmospheric pressure. So again, we're seeing this relationship with pressure and normal boiling point, again, because that's going to be important for us with phase diagrams. Normal boiling point, seeing this term again, is the boiling point at 1 atmosphere. So when we say the normal boiling point, we know that the vapor pressure of the liquid is 1 atmosphere. We know that the external pressure is 1 atmosphere. We're saying that's what normal in this context means. And a little bit of a note on actually going back to heating and cooling curves, but we have superheating and supercooling. And superheating is actually a phenomenon that happens when you heat a liquid and you actually heat it past its boiling point, meaning if we think of water, and this can happen, it's sort of just almost an irregularity of substances. If you were to heat water past 100 degrees Celsius, but it's still liquid, it hasn't yet begun to vaporize. And supercooling is cooling a liquid below its freezing point without it becoming a solid. So it would be taking liquid water and cooling it down to below 0 degrees Celsius, and it has not yet frozen. And how we see that manifested in a cooling curve, I'll do the supercooling as an example. So we have our axis, we have temp and time. And we'd expect water to freeze at 0 degrees Celsius. But the liquid actually cools down below 0, but then it will actually go back up. So it freezes here. This little dip right here, where it's sort of where it's still a liquid phase, but then it dips below the freezing point, but then it sort of returns back to the freezing point in order to undergo the phase change. That's supercooling. And It's not as uncommon as you'd think. It's essentially almost if the IMFs get somewhat disturbed and the liquid can't set up the necessarily intermolecular forces to freeze, it has to almost return to its freezing point in order to do that. But the point that I really want to make about all these phase changes is that when you look at the definition of melting point, when you look at the definition of boiling point, when you look at critical temperature, pressure is a major component of that. We're talking about pressure in all of those cases. Pressure has an impact on boiling, pressure has an impact on melting, pressure has an impact on a liquid turning into a gas on that highest temperature at which a liquid can stay as a liquid. And we need a new graph to illustrate this because a heating curve is only time and temperature, right? A heating curve and a cooling curve, they're only time and temperature. They do not take into account pressure. So a heating curve cannot describe these relationships, so we need something new. We need something called a phase diagram. And a phase diagram is simply a chart which summarizes all the conditions at which a substance can exist as a solid or liquid or gas, meaning we have a plot now of temperature versus pressure. So the heating curve doesn't have that, right? A heating curve is just temperature versus time. So this is different from a heating curve. And the way that we read a phase diagram is definitely, it's very different than how we read a heating curve. Solid lines, you're going to see solid lines on a phase diagram. Solid lines are all the temperatures and pressures, so temps and pressures, where there is a phase change. So every time you see a solid line, it's basically the summation of all the points, all the temperatures and pressures that you can get a phase change occurring. We have something called a critical point, and this is a new point that, based on the definitions we've seen, and it is truly one point, but your critical point is your critical temperature and your critical pressure. So it's a point on there where basically that's the highest temperature at which we can be a liquid, and it's the pressure that's associated with that. But we also have something called the triple point. And the triple point is the temp and pressure, because remember, these are temps, these are all points on a graph, on this graph are temps and pressures. It's the temperature and pressure where all three phases meet, meaning there is a temperature and pressure for all substances where you're going to have all three phases coexisting. You will have all phase changes occurring at once, and I'll show you a video of that tomorrow. So phase diagrams look like this. This is a classic phase diagram, and they will all have this sort of line and VE shape. So first of all, lines. All the lines that are on the phase diagram, here, here, here. Remember, lines represent phase changes. So by going from this region to this region, we have melting / freezing. And all the points on this line would be vaporizing / condensing, because this first region of the phase diagram, these represents temperatures and pressures at which the substance is a solid. Everything that's in this first region here, that's your their temperatures and pressures under which your substance will be a solid. This region here, these are all the temperatures and pressures at which your substance is going to be a liquid. And then this last region, these are all the temperatures and pressures under which your substance will be a gas. So the lines between these regions represent the phase changes. Temperatures on the x-axis, pressures on the y-axis. As we move between these regions, we are undergoing a phase change. Notice too that down here, where we're separating the solid region from the gas region, that's going to be our sublimation points and our deposition points. But more than that, the special points that we talked about, you'll notice that the vaporization line between separating liquid and gas does not extend indefinitely. The solid to liquid line does, right? This sort of keeps on going, but this one stops. So where it stops, that's our critical point, and past that, that's where we actually start to have plasma. Basically, that's where temperatures and pressures get so high that we can no longer keep the molecule intact. That's where electrons start to fly off of the atom, simply because we're under such crazy conditions. And then the triple point, see where all three lines come together? So remember, the lines represent phase changes. So where all the three lines coalesce, that's your triple point. So that's your temperature and pressure under which you have all three phase changes occurring at the same time, where all phase changes are occurring at the same time, all three phases are coexisting. So looking at the phase diagram of water, just pointing out a couple of the key points. First of all, 1 atmosphere, when the pressure is 1 atmosphere. So if we look at where the solid to liquid line, where that point is at 1 atmosphere, and then you go down, this is our normal freezing point for water, or a normal melting point for water. That's the 0 degrees Celsius that we're used to seeing. So when we're under 1 atmosphere of pressure, water will melt, or water will freeze at 0 degrees Celsius. And again, same thing, looking at 1 atmosphere for water, looking at where the liquid region meets the gas region, that's the normal boiling point, so that's the 100 degrees Celsius. But if we weren't at 1 atmosphere of pressure, like say we were right here, right, then those melting and those boiling points would change. So we're seeing this difference, this impact of pressure on where the phase, on what temperature the phase changes occur at. And we do have a triple point for water. Every substance is going to have this triple point. Now, it's incredibly low pressure. You have to drop your water down to 0.006 atmospheres, and the temperature has to be also very low, and it's very precise. But at those particular sets of conditions, your water will have all three phases existing at the same time. And then looking at the phase diagram of carbon dioxide, what I want to point out here is where 1 atmosphere is. And with CO2, what you notice is that 1 atmosphere falls below the triple point. So the triple point is here, meaning at 5.2 atmospheres, that's where you have all three phases meeting. But this means for us that under normal atmospheric pressure, carbon dioxide will not melt. Carbon dioxide will only melt above this pressure, because that's when you have the liquid turning, the solid turning into the liquid. But if we're below that point, which we are with carbon dioxide under normal atmospheric conditions, your carbon dioxide is going to sublime instead of melt. So you have the solid turning into the gas. So this is essentially telling us that under sort of normal room conditions, we won't have melting CO2, we'll have subliming CO2. So just the the last slide for this video, going over a phase diagram and asking a series of questions. So this is carbon dioxide's phase diagram. Can you find the triple point? So these are sort of things that you should be checking as you go along. Triple point for carbon dioxide. All right, it's going to be right there. It's going to be at 5.11 atmospheres and minus 56.4 degrees Celsius. Can you find the critical pressure? So we want to look at the critical point for that. A critical point is where our liquid line, our liquid to gas line ends. So the critical pressure would be the pressure associated with that. So that would be 73 atmospheres, which is very, very high. The critical temperature, again, that would be the temperature associated with that last point right here. So that's 31.1 degrees Celsius. Where fusion occurs. Remember fusion, that's another term for melting. So we want to look at the line that separates the solid and liquid regions. All of the points along this line right here, that's where we're going to have fusion. So they represent all the temps and all the pressures at which fusion occurs. Where vaporization occurs, that's boiling. So all the points that are along this line right here, that's where vaporization will occur. Those are all the combinations of temperatures and pressures that allow carbon dioxide to boil. Melting point at 1 atmosphere. What is the melting point at 1 atmosphere? So we're looking for a temperature. So we would go to 1 atmosphere, which is shown right here. And then we'd realize that this is a trick question. And hopefully you've worked out why. Because at 1 atmosphere, what phase change is the carbon dioxide undergoing? It is not undergoing melting. Melting is along the fusion curve. We don't have a fusion curve. We only have a sublimation curve at 1 atmosphere. So There is no melting point for carbon dioxide at 1 atmosphere. It sublimes at 1 atmosphere, but it doesn't melt. So that's a bit of a trick question, making sure you can read phase diagrams. What's the boiling point at 6 atmospheres? So if we wanted to answer that, we just, approximate, okay, so 6 atmospheres is somewhere along here. And we want the boiling point, so we want to read until we get to the boiling curve right there, and then go down and approximate. So that looks like, I don't know if I'm approximating really, really roughly, maybe like minus 10, minus 20 degrees Celsius or so. It's a little tough to tell from this curve. And the last question, the critical point. So critical point again, right there. So that's phase diagrams, and tomorrow you'll be just answering questions about interpreting phase diagrams, show you a few phase diagrams, etc.